Welcome back to my channel and to the third R video tutorial. Today I want to show you how you can make Sankey diagrams or Sankey networks, Sankey charts, whatever. With Sankey networks you can visualize how something flows if you want. So for example, here you can see that's my website called baseballdashboard.com. You can basically see what happens with every plate appearance. Here, this is the New York Mets in the 2018 season. So I'm sorry if you don't know about baseball, but this is the example I have. So I will use some baseball language. So what you can see here is all the plate appearances that the Mets had in 2018. So it's 6,177 plate appearances, and you can see that 22% of the time the Mets batters struck out. So you can see this with this stream here if you want. You can also see that 13% of the time they had a single, and so on. So basically that's a Sankey diagram. You can visualize flows if you want. I took the data from baseballreference.com. They have a lot of tables with almost every stat you can imagine. So I used a lot of these tables and gathered them and wrangled with them to have what I need. So let's go to R. To get started, we set our working directory. We load the packages we need, and here I read in this data that we need to construct the Sankey diagram. That's basically a wrangled version of all these tables here. So here we will just focus on Christian Yelich. That's the Sankey diagram of Christian Yelich here. So I have to filter it out here. So if we go here, we can see now we have a data frame with just one line, one row, Christian Yelich. For a Sankey diagram, you need two data frames. You need one data frame where you put in the links, and one where you put in the nodes. So let's just make it so I can show you how this looks. So the links data frame looks like this. You have a source. It's the plate appearance. You have a target. It's the sack hits. It's a bad example because Christian Yelich didn't have sack hits. So let's go to the sack flies. The target sack flies. You have a group that as a sack, and you have a value. So Christian Yelich had 2 sack flies in 2018. I can show you that here. It's 0.3% of all his plate appearances were a sack fly. So that's what you do with the links table. A source, a target, what group it belongs to. The group matters because of the colors and how it's ordered. And a value. So here it looks a little bit complicated, but basically I'm just defining a column and I put in all I need. I really had to put in manually the name of it. Then I have the target, however I want it. You should already here consider the order of the links, of the source and target links. We will order it down here too, but just keep in mind if you do that by hand that you kind of already have in your head how you want the nodes and links to be ordered. Then we do the same with the target. I think I already said that, the group, and here I put in the value from the bad data frame I showed you before. So once we have that, we also need a nodes data table. That's a little bit easier because, of course, all the nodes are already in the links data frame. I can show you this, how this looks. And what we do here is we make a data table. We make a column called name. Then we put in as character the source column of the links table and the target column of the links table. Then we pipe this into the unique function. So if I do just this, you can see down here This is exactly what we need. But here I then order the nodes so that it looks like this. It doesn't work 100%, we will come to this, because I would like to have the home runs up here. But the Sankey Network function takes the order of the links and nodes, then iterates over with an internal algorithm to come up with what it thinks the best order of the nodes and links are. I will show you if this is bigger, it also orientates around how much space it has. If this is bigger, the home runs are actually up here. I will show you that later. So to reorder the nodes, if you want, I make a vector, a character vector, and I put in exactly the order of the nodes, how I want the nodes to be. So I do this. Now we have this vector here. This is some manual work, but I think if you want to have really nice Sankey diagrams, you have to think about how it should look anyway. So I don't know a way around that. If you know a better way to do this, please let me know. And now to actually take this order and make the nodes in this order. I hope this makes sense. We use the match function. The match function takes in two arguments. So we have the new vector, how it should be ordered, and we have the column or vector from the data frame. And you can see it should be plate appearance and then sec hit, but actually it is plate appearance and single. So if we use match, I will just execute this now. It tells me, okay, that's fine. Plate appearance is the first in the old, if you want, column or vector, and it's also the first in the ordered vector. But I want the sec hits as the second element, and now match tells me, okay, sec hits sh here is the 14th element in the original vector. So it just puts a 14 here. Same with the sec flies. Here it's the third element, but in the original it's the 15th element, and so on. So I take this, the output of the match function, and I just put it in the square brackets of data. I don't know if it's data table, but I'm telling it, okay, order the lines of nodes after this order. If we execute this, we can see now it's really plate appearances, sec hit, sec fly, and so on. And now we assign this to the nodes data frame. I can show you that we have it now in the order we want. So we have plate appearances, you can compare it to here, sec hit, sec flies, and so on. I also want to assign a group to the nodes. For that I just make another vector, and I tell it that this vector is a vector. That's what the Sankey Network function needs to work with the group variable. I show you the output in the console just for fun. You can see the elements and here the levels of the elements. That's how a vector works. If you want to know more about vectors, please let me know. I'm happy to make a video about that. We can look into the data frame, so we can see we have now the name and the group. And we also need a value column in the nodes data frame. So it's again manually here. We have to take care of the order ourselves again. We do this, we look again, we can see now we have the values. So, but as I mentioned before, we can see that Christian Jelic didn't have a sec hit in 2018. If we have that, the Sankey network would look weird. I think it would look like I think here it would just be a node that says sh with 0 or something. Because I don't want that, I use, what do I use? I use which in the following way. I want to find out which elements in the value column are less than 1, or I should also work with equals 0, or are NA. Turns out nothing here is an NA. There are some players where there are NAs, so I have this in here. So if we run the which function, we can see, okay, the first line or row in the links data frame has a 0, the 15th has a 0, XY is a catches interference, and the 23rd. So XY here is here 2 times, because once it's one time it's the target. It's a bad example. Let's look for another one. I think yeah, on base is a good example, because here I have a single as the source, and the target is that the player came on base. But then afterwards I have the source, I have on base as a source, and it turned into a run. I will show you the Sankey diagram. So here we have the link from first base to on base, first base from a single, of course, means that the player was on base. So we have single as a source and on base as target, but we also have on base as source for the target run. So that's why we have it 2 times here. Okay, now we know which lines are have the value 0 or NA. And now we just say, okay, give me every line that that's not working. Oh, I didn't define it. So just give me all lines except, that's what the exclamation mark means. So it basically means don't give me line 1, 15 and 23. I'll show you. So that's how it looks. We assign this to the links data frame, and now we can see the sec hits are gone and the catches interferences are gone. We do basically the same thing with the nodes. Guess I don't need to explain that. So there are no sec hits and there is no catches interference. So now it gets a little bit more complicated. We use match again, but the Sankey network function needs 2 columns where it shows how the link should be ordered. I will just execute this and show you, and then we talk about how I did it. So let's make this bigger. So here we are basically telling, in the background there's a JavaScript algorithm. So you have to start with 0. If you start with 1, it doesn't work. So what we are doing here is, okay, the first source, if you want, marked with 0, here is the played appearance till this line here. So that's the last 0. Till reached on error. That means reached on error. We can see that here. So that means, okay, every link here starts from the first node, if you want. So we can see here we have the sec flies, and the last one the reached on error. Then I haven't figured that out 100%, so if you know better, please let me know. But then we tell it, okay, now the sources are individually, so it's a single, a double, triple, and so on, unintentional based on balls. So we have to say 7, 8, 9, 10, and so on. It also has to correspond with the target column, but I will come to this. And till on base, because then on base is again a bigger node if you want as a source. From on base, how many are there? 1, 2, 3, 4, 5 sources. So on base as a target links to 5 sources. So that's why we should have here 1, 2, 3, 4. Oh, we only have it 4 times. 5. No, here. Is it 5? Did I say 5? 1, 2. Yeah. I don't know why this one is the last in the last row. Doesn't matter. It doesn't matter because the algorithm of Sankey Network only orientates itself around the numbers here. So we have 14 5 times. So it knows, okay, that's the same source if you want. Then again, we have 16, 17, 18. What are these called? Yeah, called stealings. They are these nodes here. And they, again, are individual nodes, so they have individual numbers. And they all link to one node called out. So that's why that's 19 here. Because that also corresponds. Plate appearances in our case are marked, if you want, with 0. But of course, plate appearances can never be a target. They are always just a source, as you can see here. But let's take, for example, a single. A single is a source here. If we look here, from plate appearances to single, here the single is a target. But it's also a source, because from here to on base, it's a target. Excuse me, it's a source. Okay, again. Here, single is a target from plate appearances, and if we look at this link, the single is a source to on base as a target. So that means here the single is a target, it has the number 7. But when we want a single also as the source, we have to take it the same, we have to give it the same number so that the algorithm knows what is going on. So this is why, I hope I've explained this so it makes sense. If not, please let me know. I can write it up in a more, I hope, easier way. But essentially you're saying, okay, what are the targets and what are the sources, and you give them numbers in the order you want them to appear, more or less. Not really, because the algorithm also iterates over it, as I said before. But as a starting point, I think that should work. That should make a little bit of sense. So how did I actually do that? I use the match function again, and I tell it, okay, I want you to, it's a little bit complicated. So take the source column from links. So here, that's where we are, and order the name column from the nodes data frame according to the source column of the links data frame. So I will just run this line so we can see what's going on. No, actually, let's run. Okay, that's the order of the source column of the links data frame, and that's the order of the node of the name column of the nodes data frame. So if we use match now, it will tell us, okay, in the name column, plate appearance is the first element in the source column, and actually it is, so I don't know, 1, 2, 3, 4, 5, 6. It is so 13 times. I don't know if I counted that correctly. So it tells me, okay, the first element of the name column is also the first element in the source column, but actually 13 times. And then it tells me, okay, the 14th, let's say 14th element in the source column is the 8th element in the name column. I hope this makes sense. Anyway, we just tell it, okay, order the, no, we don't say order. That's the order we want the source column to be for what I explained before. And because the algorithm starts at zero, excuse me, because the algorithm starts at 0, we subtract 1. So if we do that, it's the same output, but it starts with 0. I know this is a little bit complicated. It took me a while myself to figure it out. So if you want to know more about it, please let me know. It's not easy to grasp, and I myself also, my brain goes up in knots sometimes when I think about it. But anyway, now we have the order we want. We do the same thing with the targets here. Okay, so the Sankey diagram, the Sankey network function also has this mouse overlay where you can see some statistics. So what I'm doing here is I'm saying, okay, the first cell, so the first row in the first column, that's the plate appearances, but I want you to show how many plate appearances there were. So I use paste to take PA, basically plate appearances, and say, okay, total, then open a bracket, then put in the actual value of how many plate appearances there were, close the bracket and separate it by nothing. So if we do this and look at it again, we can now see, okay, PA totals 651. Now for the nodes, I also want the percentages, because maybe I can show you this before we do this, how this looks. Let me see. Okay, we're doing this, then we make our network. I hope this works. Yeah, it works, but it looks weird. Let's zoom in. Now there's nothing. Now there's just the name of the node. So it's SO, it's strikeout. But I want to have the percentages in brackets here. So that's what we are doing here. Okay, I'm saying take from the nodes data frame, start in the second line, in the second row, and all to the end. So whatever the length of the column is, and give me the first column. And from this, give me the first element, because if I don't do that, how does it look? I don't remember. Like this, and if I do it, what's the difference? There's no difference. Or is there? Let's see, we can use class again to figure that out. There should be a reason why I did that. So that's a character. And if I don't choose the first element, then it's a list. Oh yeah, that's the reason. Because if I don't use the double square brackets here, the output of this is a list. But I want a character vector, that's why if you want to extract the first element of the list. And I save this in a vector called nodes to percentiles. I came up with the word percentiles. I don't know if that's a real word. It just means put the percentages to the label of the nodes. So now I know which elements which nodes I want to put the percentages in. Basically, it's just everything without the blade appearances. And to do this for all the nodes, I'm writing a small function. A function is basically everything is a function. So also class test, it says me, okay, test is a character, class is a function. We can write our own functions. So what we do here, we say, okay, I'm defining now a function, and the function will take in one argument, and that argument I call here string. And then I save all this to percentize. So percentize will be the name of our function. Then in curly brackets, I define what the function should do. And the function should do the following. It should take the nodes data frame, then it should filter the lines to whatever string I give it here. We will come to that. So yeah, let's just say, okay, what's the string? The string is segfly. So okay, take the string segfly, for example, and filter it. And now this part here is overwrite this line with what I'm defining after this operator. This operator is from data table, where you can assign new values directly in a format like this. And what I'm telling it is, okay, paste together the string, so in this case SF in our example, then open a bracket, then take the value from the bed data frame and the column SF in our case, the 2. Take that value and divide it by the blade appearances, again from the bed data frame, and multiply it by 100. So we have percentages of how common people read percentages. And do all this here, and with the round function say, okay, I only want 2 digits. But all of this is inside of the paste function. So basically it's just, we'll say SF for segfly, open bracket, then the little calculation we do here, so the percentage of the segflies according to the blade appearances, and then make a percentage sign and close the bracket, and again no operator. And remember, that's all just a function. We can see that here now. Okay, we have to find the function percentize. Again, I have no idea if that's closely to any normal English, but that's how I named my function. And now we take this function and use it in a for loop. So here, when you remember, we defined all the nodes that we want to assign the percentages to. I'm saying, okay, start a for loop. I in all the nodes here, then we open curly brackets. And then I simply say, okay, use the function we just defined here. Because remember, we are already assigning inside of the function the new value here in this part. So I can simply say, take I in this case is every single node here, turn it into a character and put it into that function. It's a little bit abstract, I think, but it's more or less the same if we would take this part here and just, instead of a string, we would put in once. Okay, do that with a segfly, blah blah blah. Do that with a single, and so on and so on. That's a really repetitive thing, so I wrote this little function here for that. Now we just say, okay, loop through all the elements, and inside the loop use the function we defined here. I will run everything. I hope this makes sense. If not, again, let me know. Okay, now we did this and we can look, nope, wrong one, in the nodes data frame, and we can see, okay, now we have what we want. We have the stack flies and the percentages in brackets. Oh, that looks weird. Why is that? The percentage sign is outside of the... Doesn't make sense. That's what we define here. So, okay. We run it again. Let's see, yep, looks good. We look again. Okay, now it's how it's supposed to be. All right, and now we finally make our Sankey network. It took a while. I know it's a lot, but I guess you can watch the parts again you need, or watch it again. There's a lot in here, but I thought, why not go all the way and start with a real life example and not like this is the ideal Sankey network. Look how easy. Okay, we did all this. We prepared the links and nodes data frames, so now we can feed the Sankey network function with it. So we say, okay, first argument is links, and it says it's actually called, the data frame is called links. Same with nodes. Here we define the sources and the targets. That's what we did here, the complicated thing with what ID, what source has what ID and what target has what ID. So we say, okay, the source is the column ID source, the target is the column ID target. The values of the links and nodes is the column value. The node ID is the column name. The Sankey network function knows where to find which column, so it knows the node ID must be in the nodes data frame. That's why we have to define the data frame. And the node group is the column group. The link group is also the column group, but here it looks in the links data frame, and here it looks in the nodes data frame. And here I use some JavaScript to make the colors. I just googled around what a color scheme would be that I like. Just some googling, and I just say I just feed JS. Let's see what JS is. I think it just stands for yeah, it's in the both of these transform character values into actual JavaScript code. I don't know a lot about that myself. It's just if you Google for scale, ordinal, and scheme category, you can find a lot of color scales or palettes that you can use. And finally, the node padding I'm doing here is the space between the nodes. So let's run this again. And here I can also show you what I meant before. Although we ordered the links and nodes how we wanted it, it looks a little bit messy here. That's why that's because the internal algorithm iterates over the order, or it takes the order and takes a different order and iterates so long as if it thinks it has found the best solution. So if we only have this space here, the algorithm says, I think that's the best solution for this space. If we zoom in, we can see it looks different. And here it actually is how I want it to be, because if you remember, I ordered it in a way that there are, let's see if we can make it next to each other. Okay, I want the sec flies, the strikeouts, flyouts, groundouts, grounded into double plays, and the home runs. And here, when we have enough space, it really does it. The home runs are in the order I want them to be. But on my website, the algorithm says, if we load it again, I don't have enough space for what you want me to do, so I think a better solution is to put the home runs here for whatever reason. That's the internal algorithm that decides that. But the nice thing about the Sankey networks or diagrams is you can move it around however you want it. So if you want the unintentional base on balls up top, you can have it. That's really nice. So that's the result. I like it. It's a lot of work because I wanted to have my Sankey network in a very specific way, and there are a lot of values and links and sources and targets and whatnot. So that's all the chaos up here if you want. But as I said, I thought, why not do the real life example. If you want to check out, I don't know, let's see, what player can we look at? Mike Moustakas. So, if you want to check out any player from the 2018 season, simply go to baseball-dashboard.com. Let's see how he did. He turned 4% of his plate appearances into home runs. Not bad. That's not bad. What does Yelich have? Anyway, doesn't matter. I hope you find this useful. Let's look at it once more. I know it's a lot. If you still have questions, let me know. I'm happy to answer them in the comments or anywhere. And if you want to be informed about stuff I'm doing, you can join my mailing list here. If you don't like comments, you can send me a mail via my contact form on my website. And that's it for this time. If you have some specific topic you want me to talk about, please let me know. I'm happy to do a video about it. I hope this was useful. Have a good day, night, morning, whatever it is, and see you next time.